Hello. Last time I received an indication that you would like to go over a problem involving determinants. So I would like to say something about it. I'd like to explore really the simplest possible case that is non-trivial, that of a 2x2 matrix. But in that context, I'll start with the following. Given a 2x2 matrix, A, B, C, D, provide a necessary and sufficient condition for its non-singularity. Now, in some textbooks or somewhere else, you will find it as regularity in that term. So I'm going to bring some prior knowledge in order to achieve such feat. Recall that the following are equivalent for n by n real matrices. Invertibility, meaning being able to multiply a given matrix on the left and the right and obtain the identity. Non-singularity, indicating that its columns or rows form a linearly independent set, and that its unique row reduced echelon form is equal to the identity. Now, I'm going to use this one in hope to obtain a numerical condition. That is really what the determinant is for. So we'll start with the following. We'll attempt a row reduction and then see what is that is necessary in order to achieve it completely, right? And what are the conditions to make it happen. Okay, but in order to achieve it, I'm going to start by introducing some cases. I'm going to consider what happens when A is 0 and when A is different from 0. So case number 1. A different to 0. So in that case, we're confronted with the following matrix. A, B, C, D. Since A is different from 0, the following reduction is possible. So I'll multiply the first row by the reciprocal of A, thus obtaining 1 B over A, C, D. Now, from this one, I will apply the following elementary row operation. To row number 2, I subtract C times row number 1, thus obtaining this 1 B over A, 0, D minus C times B over A. And now, from this point, I'll see, in order to obtain the identity matrix, I must have that this entry is non-zero. Why is that? So that it will have a reciprocal and then I will be able to continue with the reduction. If this was 0, then I will have a row full of zeros. And now that would indicate that the columns, in this case the rows, are linearly dependent. So in order to achieve this, to continue and obtain the identity, we must have that D minus C times B over A is different from 0. Equivalently, I will have that A D minus BC is different from 0. Now, let me explore the second case. What happens if A is identical to 0? Well, in that case, we're now confronted with the following matrix. We would have 0, B, C, D. Now, if this is going to be an invertible matrix or equivalent in row reduced echelon form to the identity, we should have that both B and C are equal, I'm sorry, they're different from 0. Why is that? Because if either B is 0, then we'll have a row which is full of zeros. Or if C is equal to 0, then we'll have a column which is, well, full of zeros. In either case, it will be possible to obtain a reduced form equal to the identity. So, in top of that, we should say this. Then, to continue with the reduction, we must have that B is different from 0 and C is different from 0, right? That is the condition. And then, of course, once we have that available, then we can exchange the rows and obtain something along these lines. So CD, 0B, and then from here, we'll see absolutely no restriction, because now we'll have 1 over C on row 1 and obtain 1 D over C, 0B. Then we'll make this a pivot, and we'll make the following operation: 1 over B on the second row, and we will get 1 B over C, 0, 1. And then from that point, right, use this one to eliminate this entry and apply the following operation to row number 1. We subtract D over C of row number 2, thus obtaining 1, 0, 0, 1. Data. Now, all of these operations that we have here are reversible, right? But let's explore the condition. The same happens here. Is there a way to codify this in a different format? Of course. We could say, for example, that the product of B and C is different from 0, because a product being different from 0 means that every factor should be different from 0, because we're working with real numbers. So this is equivalent to say, right, this condition, that the product B, C is different from 0. And now let's put it in the context. This is the same as to say that negative BC is different from 0. There's really no effect on doing that. And now I'm going to introduce a fancy 0 into this condition. So we'll have 0 times D minus BC is different from 0. But look, now what we have all together is that, well, look, A is 0, A is present here, even when it's different from 0. So overall, we can conclude this. The matrix is non-singular if and only if we have that AD minus BC is different from 0. And this is the type of numerical condition that we were looking for. And if you, well, if you pay a little bit of attention to the other videos, you would say that this is also the determinant for a 2x2 matrix. So the question of what is that the determinant determines, it determines whether the matrix is singular or not by making a comparison with 0. Okay? So that's it for the moment.